All right, let's get this going. Does somebody have a question? Like, I can do an optimization problem. If an honors kid's watching, I can do a limit problem. Like, let's get some stuff on the board so we can get ready for this test, huh? All right, oil rig problem. Let's do it. So, I think I have the numbers memorized. We have the oil. Okay, I gotta mute the one on my computer because it's gonna be super annoying. Also, this marker doesn't work. Big surprise. So, let's find what it does. Tight. Oh, it works really well. Okay, so oil rig problem. So we have our oil well. Let's call that OW. That's the oil well. And that is located 9,000 feet from the coast. So that's 9,000. Okay, this is our coastline. Okay, so this is the coast. Okay, let's do that right here. It's the coast. And the coast is 13,000 feet down coast. We have the refinery where the oil's going. Okay, so this is 13,000 feet right there. So we know that it cost $18 per foot to put pipe in the ocean that's going to take oil from the well to the refinery, and it cost $8 per foot on land to put down pipe that's going to take oil to the refinery. So we're trying to figure out the best possible way to have the pipe strike the land and then go from there to the refinery. We're not sure what that is. So we're just going to draw a general line and say it's going to strike somewhere. We're not sure exactly where it strikes. So this distance, that's varying. We're not sure what that distance is. When something's varying, we can just give it a variable, call it a variable. We'll call this x. X feet. Okay? So then, if this is x and this is 13,000, right? You want to figure out what this is. We are just going to cut out x from 13,000. So this represents 13,000 minus x. So the whole point of these optimization problems is we're trying to find a way to model the situation so we can graph it, because then we can either maximize it or minimize it depending on what we're trying to do. In this case, we're trying to minimize cost, so we want to graph a cost equation so we can graph it and look for a minimum. So what we have right now is we have this distance, and this distance is the one we're worried about because that's where the pipe is going. So we need to know what is this distance, and that's where we use the Pythagorean theorem. Okay, so let's just call this like W for now. We're eventually going to erase that because we're going to solve for W. By the Pythagorean theorem, 9,000 squared plus x squared equals W squared. So if we want to know what W is in terms of x, then we can just square root to solve for W. We know that W equals 9,000 squared plus x squared take a square root of that, and that equals W. That's as simplified as that's going to be. We can't simplify it anymore. So we're just going to take that and plug that in for W right here. So we get that the distance traveled, or the distance the pipe is in the water, is square root 9,000 squared plus x squared. Okay, that's this, right, is this. So then, to make our cost equation, we know our distances based on x, and we know how much it costs per foot. So we have c of x equals, okay, 18 times square root 9,000 squared plus x squared, okay, plus, all right, then we know our distance on land is 13,000 minus x, so I'm actually going to write this somewhere where I have space to write it, like maybe down here, okay? So we have c of x, again, equals 18 times square root 9,000 squared plus x squared. And then our distance on land is 13,000 minus x, and it costs $8 per foot. So we get 13,000 minus x. So this is what we want to graph. You are going to plug that into Desmos and look for a minimum. That's going to tell you the minimum possible cost of our job of putting pipe from the oil well to the refinery so we can get our oil to the refinery as cheap as possible. So you should plug this in now and see what you get. The first number is going to be our x value, right? The first number in your coordinate point is how far down coast are we hitting the coast, right? The y value is going to be that minimum cost you're looking for. So plug that in. And then I'm going to talk about the only difference between this problem and part B, which is talking about the person going from the refinery to the oil well. Okay, 2b is a little tricky because it wants us to, where'd my marker go? Find. Basically, we have a given amount of material. And we want to know if there's any way we can construct that material so that it will hold 30 cubic inches of liquid. So what we want to do is we want to say our surface area, which is 56, I believe, is 2 pi r squared plus 2 pi rh. Let me double check that number. Okay, nope. Sorry, this is different. This is saying that we want to know if we can produce a can that will hold 30 cubic inches of liquid. We want to know what's the minimum amount of surface area. So, what we do instead is we set our volume equal to 30. So, a volume of a cylinder is pi r squared times height. And we want to know what is the minimum surface area possible, like the minimum amount of material we can have to create a container that's going to hold that amount of stuff. So we say the surface area is equal to 2 pi r squared plus 2 pi rh. So what we want to do is we want to be able to graph surface area, which has currently surface area itself as a variable, and then there's 2 other variables for a total of 3 variables. And we can only graph if we have 2 variables. Luckily, we have some information here that's going to help us eliminate one of the variables here. So we have that the volume is equal to 30, and because we have that given information, we can also say that height, we divide by pi r squared on both sides, is equal to 30 over pi r squared. That's what our height is, given that our volume is 30. So if that's our height, we can take our height and plug it into our surface area. Get surface area equals 2 pi r squared plus 2 pi r times 30 over pi r squared. Okay, so this is good because we've eliminated h now. We only have surface area and r's in there. So then when we graph this in Desmos, Desmos doesn't recognize r as a variable. So, I mean, it does, but not as like an independent variable that it will graph. So in Desmos, what we're going to type in is we're going to type in 2 pi. If you just type pi, it'll make a pi symbol. X squared plus 2 pi x times 30 over pi x squared. If you type that into Desmos, the first number you get is going to be the radius of our can, and then the second number you get is going to be the minimum surface area. So I'll give you a second to catch up, type this in, and then I'll show you how to find the height after you know the radius and the surface area. So when you type this in, you're looking for the positive values only because it doesn't make sense to have a negative volume. So I got that the radius equals 1.684 and the volume equals 53.448. So basically what that's saying is we have a cylinder that has a radius of 1.6884, right? That's our R. We don't know is what our height is. That's going to lead to a volume that we're looking for. So we can use our volume equation now, or sorry, our surface area equation. Sorry if that was confusing. Surface area is what we found. And we can plug that into our original surface area equation. So we get 53.448. That equals 2 pi. We know what the radius is 1.684 squared plus 2 pi 1.684 times h. So what we have to do is we have to solve for h. And what I just remembered is we already did solve for h right here, right? H equals 30 over pi r squared, right? So what we can do instead is we can just say h equals 30 over pi times 1.684 squared. And that would give us our answer as well. You just have to type that into a calculator. I'll link the video where I worked this out with the full answer if you want to watch it again and get a different look at this problem, but that's pretty much to be worked out. All right, Gabe. So hopefully you figured out that a is 3 because we're taking a limit as x approaches 3 of 1 over a plus x plus a, right? X plus a minus 1 over 6 over x minus a. So a must be 3 to get 0 over 0 when we plug in 3, right? So we're going to replace a with 3. Okay, because now when we plug in our limit, we're going to get 1/6 minus 1/6, which is 0 over 0. And then we get, it's 0, sorry. And then over 0, which is 3 minus 3. Okay? So we want to manipulate this because we want to find an x minus 3 that's hiding up here. Because it must be if there's a hole at 3. And the only way we can really manipulate this, there's nothing we can do except find a common denominator. So our common denominator is going to be 6 times x plus 3, because this one has a 6, this one has an x plus 3. Together, 6 times x plus 3. This one's missing a 6, so we end up with 6 over 6 times x plus 3 minus x plus 3 over 6 times x plus 3. And then the whole thing is still over x minus 3. Okay? So the thing is, we have to distribute this negative to both pieces. So we're going to get 6 minus x minus 3 over 6 times x plus 3 over x minus 3. Okay, that equals, 6 minus 3 is 3. So we get negative x plus 3 over 6 times x plus 3 over x minus 3. So now we factor out a negative. We're going to get negative x minus 3 over 6 times x plus 3 over x minus 3. So this is the part that I think you're confused about. So if we want to do copy, switch, flip, we have to say that x minus 3 is over 1. So this is our rule for dividing fractions. We have one fraction divided by another fraction. So we can copy the first one, negative x minus 3 over 6 times x plus 3. This is equal. Instead of dividing, we're going to switch to multiplication. That's why it's copy, switch, flip. I always said copy, dot, flip, because we're multiplying, so it's dot, right? And then we're going to flip x minus 3 over 1 to 1 over x minus 3. And then the x minus 3's can cancel. So we're left with negative 1 over 6 times x plus 3. Now we can plug in our 3 because our whole was canceled. So we plug in our 3. We get 3 plus 3 is 6. So our final answer is going to be negative 1 over 36. Okay, let me know if you have clarifying questions. Maya, say hi. Here, jump up. Hey, come on. Come. Hey, say hi. Say hi. Say hi. Come here. Hey. Look, look, look. Hey, look. Maya, look at the camera. Look at the camera. Okay, get out of here. Get out of here. I gotta help him with math. Go, go, go. Go, go, go. All right, Caroline, so number 3 is saying we have, what is it, a whole and 2 zeros? Oh, a hole and two vertical asymptotes. Okay. We have a hole and two vertical asymptotes. So, to answer this question, let's make an example. So, we have a hole. Holes are on top and on bottom. So we just need a matching factor on top and on bottom. It doesn't matter what the second number is, as long as it's the same for both. Okay, there's our hole. And then we have two vertical asymptotes. So again, this number doesn't matter as much as long as we have two factors down here that are different. Okay, there are our two vertical asymptotes. Okay, right now, on top, we have a degree 1, and on bottom, we have a degree 3. Okay? So if we were to plug in infinity right now on an infinite scale, right, we would end up with 1 over, because these cancel, right? 1 over, well, infinity, which is 0. That's our horizontal asymptote right now, is 0. So what we want is we want enough factors on top that when we plug in infinity, we're going to end up with infinity on top, because then there's no horizontal asymptote. So if we add a couple factors in here, okay, if we add like x plus 2 and then like x plus 5 and x plus 7, okay, again, on an infinite scale, if we plug in infinity, only at infinity, these cancel. Also at infinity, x plus 2 and x minus 3 are basically the same. So they're going to cancel each other out. And then at infinity, x plus 5 and x minus 4 are also basically the same. Like, infinity plus 5 is basically the same as infinity minus 4. So those also cancel out. At infinity only. So right now on bottom we have 1, just 1, because once they've canceled, they just left a 1 down here. On top we have 1, 1, 1 times infinity. So we end up with no horizontal asymptote now, because 3 of the factors have canceled out and there's 1 left over on top. So the minimum number, or the minimum number of zeros, right? That's what it asked. Oh, this is how many zeros, right? So we needed 3 zeros, zeros are only on top, to create a function where we had more factors on top than on bottom. All right, so then that's it. It's just 3 zeros, and then this is the reason why. Now don't forget that when I cross these out, that's only on an infinite scale that I was able to cross out all of them. Because we're looking, that's where horizontal asymptotes show up, when x gets really, 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 really big. Okay? Let me know if you have any clarifying questions.